Okay, as promised, we are going to start first order PDEs today. Okay, so although you may be thinking that you have been introduced to it for the first time in my class, but you have already dealt with the ingredients of it in our previous classes. Okay, fine. So a first order PDE in two independent variables, say x, y, they are independent variables, and a dependent variable j, they are dependent variables. Sorry, j is a dependent variable, is defined to be of this form. This is equal to 0. So let me call it 1. Let me call it 1. Okay. So where your f, it is a function, defined in some region, omega tilde in R5, right? And in R5, what we are going to do, we are going to designate a point in this form. A point will be something like that. Is it okay? Fine? And then what is going to happen? A solution of 1 is going to be of the form z equal to f of xy, z equal to f of xy. Suppose you call it 2, where f is a function defined in some domain omega in R2. Is it okay with everybody? And of course, here, because I am considering the first order derivatives of z in this equation, when I define the solution of this equation to be in this form, I am going to also add another extra condition here is that f, it has to be C1. F has to be C1 in that domain, omega. Is it okay? Fine. And again, like say, we are not only going to call this solution of this equation, but it has to satisfy certain conditions. So, what are they? Number one, for all xy belonging to the domain of small f, your this one, xy, z, zx, zy is must belong to the domain of capital F. Okay? And then number two, if you substitute this expression, in this equation, it must reduce to an identity. Okay? I think they are to be expected, right? So this is the formal definition of a first order partial differential equations in two independent variable x, y, and a dependent variable z. Is it okay? Fine? Okay, fine. So now, as I have been complaining, or you may have been complaining behind the scene, I haven't classified the PDEs because I didn't formally introduce you to a PDE. Today I'm doing it. So you can classify, I mean, again see, this classification is not unique. Classification of, because I am dealing with only first order. Okay, first order PDE. So I'm going to follow what this Thaw and Jack Managlo has followed in their book. So number one, maybe your quasilinear. So it is going to be of this form, something like your P x y z z x q x y z j y. This is equal to r x y z. Okay. So in fact, this is what we are going to deal with. This is what we are going to deal with in today's class. And number two, you may have your almost linear. So it is going to be something of this form, like these functions. See, earlier p, q, and r, they were functions of x, y, z, and later on you are going to see that they have to be c1 of class c1. And if suppose these coefficients, suppose they are functions of x and y, I am going to deal with this in a short while. But say r still remains a function of all the three variables. So then this one is almost linear, and then linear, they'll be of this form. You already know it probably, but still, for the sake of completeness, I am doing this. Why write PQ? Let me write it as AB. ZY, because I want to write it in general form. That is why I am introducing this variable as well. And this is okay. And I'm not going to give you examples. I mean, you have already seen it. I mean, many a times probably, and you can find them in this book also. Later on, we are going to deal a lot with these two cases. So you will find out enough examples for that. Okay, fine. So this is about classification. So now, and again, what I request you, like even though I haven't told you in my last few classes, please try to do as many exercises as you can from the related chapters that are there in that book. Okay. So this is about classification. So now let me come to general solution of this one. Okay, and let me call this as 1. Let me call this as 1. Okay. Again, what I am going to do here, I am assuming that PQR, they are some class C1 function in some domain. Let me call it omega tilde, where this omega tilde is a region in where? Region where? R3. Okay. And as before, a function this again defined in some omega in R2, and of course a class C1 function, okay, defined in this way is we are going to call it a solution of 1 if as before it satisfies this condition. Say for all xy belonging to your omega, what happens? Your xy what? Yes? What should be here? F of xy, yes. F of xy belongs to omega tilde. And number 2 again. I mean, once you substitute this solution in the given differential equation, it reduces to an identity. That's it. It reduces to an identity. So far so good. It sounds so easy, right? It sounds so easy. Okay, fine. So now let me just okay. I will try to give you some geometry visualization ideas. Okay, fine. So my equation is PDEs. And yeah, and another information I forgot to tell you is that the functions PTR in omega tilde, at least one of them is non-vanishing. Okay, so that condition has to be there. And then suppose your z equal to f of xy is a solution of this equation. Okay, is a solution of this equation. So now, what is happening here? Obviously, if this is a solution of 1, what I can do? I can conceive z equal to f of xy as a surface in R3. Is it okay with everybody? Right? Isn't it? Right? Yes. It is going to define a surface in R3, and that surface is called a solution surface of 1. Solution surface of 1. Okay? So the surface represented by the solution of 1 is called a solution surface of 1. Fine. And again, what I can do if I decompose 1, you can see that I can simply write it as sorry. Okay. Okay, fine. I can simply write it as this, isn't it? Yeah. Right? So that means if I had like say if I define a level surface, I define a level surface this for some function u of x, y, z in such a way that your u, x, y, z, this is equal to your what? Maybe. Okay, fine. I think you will understand. Z, right? So then what is happening? What is going to happen? So this is going to simply indicate that this is simply your ux, uy, uz. Is it okay? Fine. Just a minute. I have already written this. Okay. So is it okay with everybody? Is it okay with everybody? Because see, zx, zy, they are nothing but fx, fy, isn't it? If I write it in this way, is it okay?
Yes, sir.
Fine. So that means if I define V to be the vector field given by PQR as its components, so that this is going to be satisfied. So then, can you give me a relationship between the vector V and this surface? Yes. Can you now relate the vector V to the surface given by this?
That vector is orthogonal to that surface. That is dot product is also not orthogonal, it is tangent.
Okay.
Is dot product with the gradient is it is tangent to the surface.
So that means it is an what? This surface is an what surface? Exactly. Exactly. Right? So that means that gives you another information that if I find out the solution of this equation in this form, which is nothing but a solution surface, right? The solution surface is nothing but an integral surface of the vector represented by these components of the vector field represented by these components, and that integral surface is given by this equation. Is it okay with everybody? See, same thing. Only thing is that now my uxyj is in this form. That's the only slight subtle change we have made here. Okay, fine. So now what I'm going to do, I'm going to introduce you to some theorems. And just a minute, let me see whether I have missed anything or not. Okay, fine. So, like there are going to be two lemmas. There is going to be one lemma and one theorem. That theorem I am not going to prove, and I'll tell you why I'm not going to prove it, because we have already proved it in some way. We have already proved it in some way. Okay, fine. Lemma. Okay, so let u be in your C1 omega tilde, and of course omega tilde is some reason in R3. Let this be in this, and this is nothing but this where maybe I should write it, where omega tilde as a subset of R3 is the domain of the functions PQR, of the functions PQR, and of course which defines, see in that Thor book they have referred to so many equations like that has been used. We seem to get lost in those, so that is why I'm writing it on my own, defining the vector field, of course, V equal to PQR, V equal to PQR. Okay, fine. And then suppose that at every point of the level surface given by this u xyz equal to 0, u xy equal to 0, the following holds. What are they? Number one, of course, Pux plus Qey plus Ruz, so this is equal to 0. And number 2, this is a very big condition. We are going to make use of it. This. Can you tell me why this condition has been brought in? Use it not equal to 0. Yes? Any idea? Yes. So implicit function theorem, what is that going to do?
If z is non-zero, then we can write z equals to
F of xy. Okay, and that is going to be a solution of a given differential equation. That's it. Okay. So whatever I am going to write holds. So then what happens? This is exactly what you have told. So then one implicitly defines one j as a function of two variables x and y, okay, and did I tell you about general integral? Okay. See, I am not sure. Just a minute. What I told you. See, had I written the did I write finding general integral of this, or I wrote finding general integral of this? So this is basically about finding general integral of this. You should remember that. And this function satisfies the PDE, this one. P zx plus q zy equal to r. This is what it is, and you will see that. I mean, this is going to be straightforward. Okay. Okay, fine. So basically, what is given here? You will be given a differential equation. Okay. So then, what we are going to do? We are going to find a solution to this differential equation. But what we are going to do, rather than solving it through some method, we will try to solve this one, which is going to give me an integral surface corresponding to this vector field, okay, and because this uz is not equal to 0, that is going to give me an implicitly what z as a function of two variables x and y. That's it. And you will see that it's very straightforward. So proof is pretty straightforward. Okay. Say we have been given that uz not equal to 0. Okay. So then what is going to be your zx? So zx is going to be simply what? Isn't it? Fine? Okay? There are so many guys in the room, although they are not in the classroom, they are in the virtual classroom and nobody is answering it. So,
yes, it is.
so your what is going to happen? Okay. So from here, what I get, Pzx plus Qzy. So this is going to be what? This is going to be your minus PUX plus QUY by UZ, right? And we have already been given this condition. And from this condition, minus of this is simply what? RUZ, right? So this is equal to RUZ by UZ. So this is equal to R. So that proves the theorem. Okay, fine. So this is done. So next, again, I am going to, write a theorem. I am not going to prove it as promised because we have already done that part. Just I'll state the theorem so that we can apply it in solving differential equation of the form Pzx plus Qzy equal to R. Okay, fine. That's what we are going to do. Okay, fine. So, theorem. To be two functionally independent solutions of this. You know what the equation is going to be. PUX plus QY. So basically, there are two first integrals of the vector field V given by PQR. Okay, fine. Let me call it A. Okay, and of course that is in some R3. Okay, and let your f of u1, u2 be an arbitrary function and arbitrary function of two variables. And now consider the level surface, this one. You already know it. X, Y, Z. This is equal to 0. Let me call it B. Okay. Then on every point of this surface having non-zero normal component, non-zero normal component. Non-zero normal component means, just a minute. Basically, this non-zero normal component having non-zero Z normal component. Z normal component. Is it okay? Because what is going to happen? See, suppose this one, I call it, say, something like f of x, y, j equal to 0. Say. Okay. So then your grade f is going to define a normal at each point, right? Each point on that surface, isn't it? So obviously this is going to be a vector. This is going to be a vector, right? So this component is non-zero. Is it okay with everybody? Fine?
Yes, sir.
Right? Non-zero Z component, Z normal component. Normal component. Your this equation B, this equation B defines Z.
Sir, can you repeat that thing once again?
Yeah, sure. Thanks. Let me just write it down. Define Z implicitly as a function of x and y, and what happens? This particular function, this function is a solution of this equation, zx plus 2 zy plus r. Okay, I'll come back to that now. Okay, see here what is happening? I am taking f of u1, u2. It is an arbitrary function of two variables where the argument of this function, it has come from this functionally independent solutions of this equation, right? u1 and u2. So this is what it is. This is the level surface that has been eked out of those two, functionally independent solutions, right? So obviously, this is the left-hand side. It is eventually going to be a function of x, y, z, isn't it? Right? Is it okay with everybody? Right? Say if I write it something like this, say, I can write it as a function of x, y, z, right? So this is going to be f equal to 0. This is going to define a level surface, right? For the function f. Is it okay? Fine. So then on that level surface, at each point, I can have a normal which will be defined by grade f. Okay. I am assuming that in that normal vector, the third component is non-zero. That is what it is. So this is what is the meaning of this. Then on every point of this surface having non-zero normal component, right? Whenever it has a non-zero normal component, B is going to define implicitly. So this relation is implicitly going to express J as a function of x and y, which in turn is going to be a solution of this. In fact, I'm leaving it as an exercise for you because this has already been done before. Okay, this has already been done before. Okay, so you will please go through whatever I have taught earlier and you will find your answer here. Just you have to reframe it. Okay, so basically what is this theorem telling you is that in order to solve this equation, what we have to do, we have to find out two first integral of this equation, and then what we'll have to do? Yes? Then under this given condition, right, I would have an explicit expression of J as a function of x and y, which is going to be a solution of this. Okay, so let us try to do one exercise, then it is going to be clear to you. Maybe I'm going to give you two examples. Okay, and remember the expression B. It is called a general integral. For this equation. Is it okay? Fine. So let us try to work it out. And I'll be doing one more theorem later on if time permits. So then I think you will appreciate it more what we are trying to do. X zx plus y zy. Okay, so you find a general integral of this equation. So what? Simply find out u1 and u2 in such a way that they are functionally independent, right? And then construct an arbitrary function, right? And from that function, you just extract out an expression for j in terms of what? Z in terms of x and y. So you know that this is pretty straightforward, right? Like what I'd like to do. I'd like to see. Just a minute. You may be thinking that how can I rope in this? How can I rope in this equation, right? See, you are simply concerned about the components of V. That's it. Just because you have a new variable here, u as a function of x, y, z, you shouldn't be afraid of that. That is always going to come, isn't it? Because what you do, if you want to find out an integral surface from this equation, what you simply do, you simply solve dx by p equal to dy by q equal to dz by r, isn't it? That's it. I already have pqr here. P is x, q is y, r is z. Is it okay with everybody? Right? That task is not difficult. In fact, it is one of the easiest tasks, I guess. Right? Okay. So, you know, like I can get from here, it is easy to see that I can get x by y, maybe y by z. This is equal to 0. Right? Isn't it?
Yes.
Right? And I mean, now you construct any function out of this in such a way that you can express z as a function of x and y. That's it. Is it okay? Because this problem is already worked out in your book. I'm not going to do it further. You can have a look. Let me do one which has been given as an exercise. Can you give one? Like you can choose something else also. I simply want z as a function of x and y. What do you want to do? From here, say from here, I can have something like this also. F of x by y, z by x or z by y also I can have. This is equal to 0. Okay. So if you equate these two, right? So then this is going to give you what? Z equal to x, and of course since y was present, so you may take y greater than 0 or y less than 0 in order to find out the domain, your omega. Is it okay?
No, it's
Somebody said no. Yeah. Can you tell? Yeah.
so why doing like that is not clear.
No. What I have done here, say this one was u1, this one was u2, right? Isn't it? So I have simply chosen the function, say u1 minus u2 equal to 0. Okay, fine. I have chosen capital F u1 comma u2 as u1 minus u2 equal to 0, right? And that is going to give me x by y equal to z by y. Although I can equate, I mean simply z equal to x, right? But I shouldn't, not completely. I in no way, give up the role of y here, because you can equate z equal to x only when y is not equal to 0, right? So, isn't it? and I am seeking the solution on some domain omega in R2, isn't it? Right? So I am going to choose this omega in such a way that either y greater than 0 or y less than 0. Is it clear now? Right?
Okay. So it is not a general case. You are taking a particular answer.
Because the way I have chosen this, that is why it is like that.
Yes.
You will have infinite number of choices.
Yes.
To create J, which is going to satisfy this differential equation. Is it okay? Fine?
Yes.
Okay. So now I have got yeah. Before I move to and there's one interesting observation this book has described. This book has described like see, yeah. Say, suppose, like from these two first expressions, itself, I get an integral surface where the function connected with that integral surface, it was independent of J. Okay, independent of J. So in those cases, what we can do, we can always express J as a function of, like say, if that one was the function. Okay, I am just going to give you an example. Say, suppose you have something like suppose this is equal to 0. Suppose this is equal to 0. Is it okay? Fine. So then what is going to happen? From here? And of course, I am assuming that at least one of A and B is not 0. Okay. So then what this is going to give? Your very first integral coming up of see, this is what? AXY BXY. Fine. Is it okay? Fine. So then what is going to happen? From the first two ratios, you are going to get definitely some integral surface like this. Isn't it? Or sorry, not necessarily this. Is it okay?
Yes, sir.
So basically what you are going to get, capital U XYZ equal to simply a function of xy equating to some constant, right? So then in this particular case, again the second integral is z equal to constant, isn't it? Right? So then I'll be able to write simply z equal to f of u1. But that shouldn't that shouldn't give you the impression that only when this component is 0 that is going to happen. It is going to happen for other functions also. Let me try to give you one example. In that case it may not be possible. It may not be possible, but I'll still try to give you. Sorry. Not that. Not J. Sorry, not J. See, in this particular case, J is equal to f of u of xy. F of u of xy. Okay, fine. So now, if say this is again some other function, say r of xyz, right? If it is a function of 3 variables, say. Okay, so then obviously what is going to happen from the second part, you are going to get something like u2 xyz equal to c2, right? Okay, so then obviously what you are going to get something like this. Not Z, I mean explicitly, you are going to get something like this. U1 xy. Okay, so what does it take care of? It takes care of almost linear equation. Are you getting my point now? Yes? So, for almost linear equations, you are going to have solutions like this. Is it okay? Fine? I mean, almost linear equations in this form. Okay? How much time do I have? Okay. Let me try to work out one example pretty quick. I find that very interesting. xy z square plus 1. The xy z square plus 1. xy z square plus 1. Okay? So, and again, you please check the functional independence of your integrals, first integrals. Okay? Again, here the corresponding associated set of equation is what? Okay, fine. So obviously your U1 is what? From these two? Yes, these two what? X, Y. X by Y. What about the second manipulation? Say this is giving you a clue, xy. Right? What is the total differential of xy? X dy plus y dx. Isn't it? Fine?
Yes, sir.
So if I do y dx plus x dy, obviously xy, xy. So 2xy, that is going to give me dz xy z square plus 1. So this implies d of xy by 2, this is equal to dz by z square plus 1. Okay, fine. So what I can do, I can write, see from here I am going to get what? Tan inverse z. Is it okay? And from here I am simply going to get xy by 2. So obviously you can write something like z equal to 10 xy by 2, right? Z equal to 10 xy by 2 and plus some constant, isn't it? I mean, see, again, how you adjust the constant, it is up to you. Is it okay? So that is why what I can do, like say u1 equal to x by y, u2, I may write it as something like z minus 10 xy by 2, right? And from this, what I can do, as you have already seen, here these two simply involve functions of x and y only, right? So I can easily write it as something like z xy by 2, and this is equal to some function of x by y. So my solution is something like this. X by y. That's it. Okay? Fine. and please try to do as many examples as possible. Okay, so now I am dying to come to this particular part. What I'm going to do, you'll understand why I'm so desperate to come to that. I find it very, very interesting. Okay. Fine. PDEs, and then this part. Existence and uniqueness. Okay. Any idea what kind of problem, I mean, or what kind of concept we are going to formulate? Yes? Anybody can tell me? Yes? Okay. It's like I'm asking and begging you for silence. Okay, don't worry about that. Fine. So, I'll try to do, I'll try to bring an analogy with the first order ordinary differential equations that we and what that we tackled in our ODE part. Okay, so if you look back, the first order ODE, it was something like this. It was something like this. You will say dy dx, okay, of f of xy, right? Subject to some initial condition is, okay, fine. This is the given differential equation, right? And this is the initial condition, okay, fine. And I called it as an initial problem. Fine, so far so good, right? That is what we did. Now, here, what we will try to do, we will try to construct an initial value problem corresponding to the differential equation given by this. Is it okay? Fine. So now, obviously, because I am trying to construct an initial value problem, so that is why I have to have an initial condition. So now, you here, obviously, what this PQR, okay, I am going to define them as some class C1 function. You know the meaning of that. In, let me call it omega tilde, where omega tilde is a reason in R3, right? And of course, I will try to seek solution of this form, right? I will try to seek solution of this form. Is it okay with everybody? For it Till now,
Yes.
right? So now I have to set an initial condition. I have to set an initial condition. Okay. So earlier the initial condition was given over R1, right? Is it okay? Initial condition was given over R1. So now, because I am seeking the solution as a function of two variables, the initial condition is going to be given in R2. Okay. So what I am going to do, I am going to seek the initial condition in some domain, say omega in R2. And what it is going to be, say suppose this is x, this is y, and this is your domain, say omega, domain of definition of the solution omega. So then this initial condition is going to be given in terms of a curve, C. Okay, now you may be thinking how the initial condition would be given in terms of a curve and eventually what we are going to seek. Okay, fine. So this curve is going to be called the initial curve. This curve C, say. And what we are going to do, as before, we are going to parameterize this C by this one, your x naught t, y naught t, right? In omega, right? We are going to parameterize. We can parameterize it through this factor, isn't it? Is it okay?
Yes, sir.
Right?
Yes.
See, initially I am going a little bit slow because you should understand it geometrically. Because now I am still in 2D. After a while, I am going to move to 3D. Okay. Fine. So, okay. And where your t belongs to some interval I, and of course your this x naught, y naught, they are C1 in I. So far so good, right? Parameterization, you guys have become expert now. Yes, you guys have become an expert in parameterization, I guess. Right? See, I have simply defined a curve in omega. Fine, but I still haven't defined any initial conditions. How that is going to constitute as initial condition. Yes, any idea how that is going to give you the initial condition? Yes?
So for this initial condition, we shall find some T naught from this interval R.
We shall find out some?
T naught means
Yes, yeah.
means our initial curve is given.
And yes, go on.
So for that we shall find some T naught belongs to this interval I. From that we should get this initial point maybe.
No, okay, fine. I understand because you were trying to relate it to initial value problem for 1D, right? See here, can you please think instead of that point, you can think about all the points on the curve.
Yes.
Right? So that is what we are going to do. That is what we are going to do. So basically what we are going to do, now we are going to introduce a new function, z naught t. We are going to introduce a new function z naught t. So basically what is happening here, if you define a new function z naught t, So that means I can seek a third coordinate corresponding to this the point, right, given by this, isn't it? So basically, by defining a new function z naught t, so what we have been doing now, let me just try to give you okay. So what is happening here? This is my curve C. Okay, let me again, maybe let me keep the point x0, y0 also here, right? It is a fixed point. So then what is going to happen from here? This curve will be parameterized by simply RT. So far so good,
Yes.
right? So now what we have done, we have defined another function z naught t. Okay, so what we are going to do, that this z naught t is going to give me a new coordinate in space. It is going to be like this. So that means if I can get a curve C tilde, let me call it C tilde, right? Corresponding to this curve C in xy plane, but this curve C tilde in xyz space, right? So that the third component of this is given by this function. So then what is going to happen? Corresponding to this, I am going to have, say, suppose this vector, let me call it, say, capital RT, right? It will be given by something like this. Are you getting my point now? Yes?
Yes.
So now, how to construct a problem? So basically now you have a curve C tilde in R3, and that curve is going to belong to this domain. Okay. So now, what we are seeking? We are seeking a surface. We are seeking a surface in such a way that this curve C tilde lie on that surface. Okay. And then what we are going to do, that surface is going to be a level surface, something like u of x, y, z equal to c, right? So then what we will try to do, under certain prescribed condition, right? So we will try to get that surface u, x, y, z equal to 0, say, as the graph of a function of two variables. Okay, so that particular function, where we are seeking the graph of a function of two variables, it is going to be a solution of the given differential equation 1. So that is what it is. See, mathematically the initial condition still I haven't defined. But I am just telling you about the construction procedure. How the overall situation is like. Like, say, mechanically we can solve equations like million times we can solve. We can get 100 out of 100, maybe sometimes 110 out of 100, right? But your geometrical concepts, it should be clear. It should be crystal clear. Okay, so that is why before giving you the exact initial condition, I am just trying to give you an overview of what is going to happen in future. Is it okay? Fine. So now I'll come to the initial condition. Okay? Fine. So obviously what I have done, I have defined another function this. So now I'll come to I'll come to the actual here. Okay. So the IVP of the equation 1 is to find a solution say z equal to f of xy, z equal to f of xy such that on the curve C your z is equal to the given function. Okay, of course, I'm going to a given function that is nothing but z, the z naught. Okay, so basically what it is telling you, I'll tell you. I'm going to repeat it again, don't worry. Okay, equal to the given function z naught. So basically, what it says is that your z naught t is f of x naught t y naught t. Okay, z naught t is f of x naught t y naught t. Is it okay? Fine. And this is my initial condition. This is my initial condition. Okay. I'll again summarize it. Don't worry. And this problem is also called Cauchy problem. Okay. Now I'll tell you again. Let me re-summarize. So,
Sir,
yes.
so why the initial condition will be like that form z naught t equals to, can it be somehow different from this format?
Okay, let me repeat it and probably then you are going to understand. Okay, fine. See, here what we have an equation like this. Fine, we have an equation like this, subject to a given curve, right? Which has been parameterized by say RT equal to x naught t y naught t. What you will be given? You will be given a curve. This was in R2, right? This was in R2. Now, along with the parameterization of this curve, or along with a description of this curve, you will be given another curve in 3D space corresponding to this one. Okay, right? You will be given that condition. Okay, so this is nothing but my initial condition. Okay, fine. Say this something like this. Okay, I mean it may not be exactly given in terms of t, but you are going to be given that in terms of some functional relationship. Okay, but again that functional relationship that is going to hold only along this. Say I am seeking a solution in this domain omega. Is it okay? Fine. But what you will be given? You will be given only at some points. Earlier in 1D case, you were given only at 1 point, right? You were given the initial condition at only 1 point. So now I will be given an initial condition along a curve. Remember that 1 point was x naught, right? You were given something like this. Why not? Isn't it? Fine?
Yes.
Now because I have been giving all initial condition along all points here, that is why the initial condition is now given in terms of j, I mean f of, I mean x naught, y naught. But it is not only given for a single point, it is given for the whole curve, right? And how can I get the whole curve? If I have some interval where this parameter t lies, by varying t, right, I can get this initial condition at all the points on this curve. Now is it clear?
Yes, sir.
Okay, but you should be able to visualize. You should be able to visualize uh, this initial condition in 3D space. So you know now that that is nothing but some curve C tilde, right, in 3D space. Okay, so whose coordinates are given by this? I mean, which is parameterized simply by this, which is parameterized simply by this. That's it. Now, geometrically, is it clear? Yes?
Yes.
Right? So, geometrically, it should be clear because if it is not clear geometrically, then I mean, it is going to be impossible for you to, like understand it. Okay. Anyway, we can memorize it. I mean, everybody can memorize it, but understanding is, important, right? And at least, I mean, like say, when you are going to go out of this institute, then I mean, I'd like, I mean, other people, other mathematicians, I mean, appreciate you that, oh, okay, these guys, they have crystal clear concept about this, okay? And also, I'll also be feeling proud because then you'll be able to tell that, okay, somebody called JCK taught you. Fine? Okay. So now, I think the theorem I'll do in my next class, but before that, so now because the initial condition is clear now, right? Initial condition is clear now. So obviously, now what I have got only a curve, right? Only a curve in space, isn't it? So now I am seeking a solution. Of this form, z equal to f of xy, right? Which is going to be a surface. Okay. So basically, the solution surface should be such that if my surface is like this, if this is my solution surface given by z of, it should be such that what this initial curve is going to lie on that solution surface. That's it. So now I hope you have understood it, because see what is going to happen later on. When I will give you this statement, all the information may not be there, but it is like hidden. So you should know that this information, it is already there, hidden in the theorem or in some of the concepts that we are going to learn later on. Okay, fine. So I think I can have a kind of curtail class here today, or can I do something else? I have got 1 or 2 more minutes. Okay, fine. So okay, fine. So yeah. So now you know that what we are trying to do. We are trying to seek a surface in such a way that a given curve lies on that. So we have already learned, isn't it, how to construct an integral surface, isn't it? We already know how to construct an integral surface. So now you may be thinking, sir hasn't taught us exactly from syllabus. Now you will realize that, in fact, I have taught you all. Now I have trained you up. Okay, so now you can tackle it. So because we already know how to do it, so exactly in that way, whatever we have learned, we are going to do it. But the thing is that because earlier, see the difference between what we did earlier we simply considered something like this. Okay, but this has some hidden information in such a way that I should have been able to get something like z equal to f of xy, right? So that is my point. So in order to have this, I will have one certain extra condition which must be satisfied. That is going to be in terms of Jacobian, and I am telling you that particular condition is a killer. It solves so many problems. I mean, we should really appreciate all those. Mathematicians who develop that. I think you will appreciate in our next class where I am going to prove a theorem. Okay. So with that note, I am going to end today's class. I'm going to end